All right, the last kind of problem that you'll see in section 3.1 are questions where we start with a graph and then think about how complicated a polynomial has to be in order to have that particular graph. So the first fact I want to talk about is the relationship between the degree of the polynomial and the number of real zeros. And remember, a zero of the polynomial just corresponds to a horizontal intercept on a graph. So we can look at a couple of examples. For example, we know a linear polynomial, so something that's a straight line. A straight line has exactly one zero, one horizontal intercept, so we can see it. And the degree of a linear polynomial is 1. And so we're off and running. There might be some pattern going on here. The thing we'll talk about next in the class in section 3.2 is we'll talk a lot more about graphs of second degree polynomials. So for example, a graph like that comes from a second degree polynomial. And let me just tell you what the equation is for this one. So this is y equals x squared minus 4. I didn't put a scale on it, but just for example, that could be the equation of a graph like that. And so notice that this graph has two horizontal intercepts, meaning this function has two zeros, and the degree is 2. So it seems like there's a connection between the number of actual zeros or x-intercepts and the degree of the graph. And that is true, at least to an extent. It is definitely true that you can't have more horizontal intercepts than your degree, but that's about all you could say. So if we can count the number of zeros, count the number of horizontal intercepts, we know the degree is at least that many. So let me show you an example of why all we can say is at least that many. And I'll just move this badly. There we go. So here's an example of a graph, and you can see it has all kinds of wiggly gyrations in it, and but it only has one horizontal intercept. So from the example we just saw, the graph that I showed you that had one horizontal intercept was a straight line. So obviously this is not a straight line. So this polynomial must have higher degree than degree 1, even though it only has one real zero. So the theory just says that the degree has to be at least as big as the number of real zeros. So all we can conclude from this graph is that the degree is at least 1. So there's one real zero, and the degree of the polynomial, the fact 1 tells us that the degree is at least 1. But that is sort of a dumb statement. The degree 1 would be a straight line. It definitely has to be bigger than that. But it is true that the degree is at least 1. So it's not that fact 1's ever wrong, it's just that it's not saying very much in this case. So FYI, this graph is the graph of this function. So it's actually the graph of a fifth degree polynomial. And so this gives us an idea of another way that we can figure out the degree. And it's based on not the number of times you happen across the horizontal axis, but rather the number of times you wiggle around. So we're going to introduce a term called the turning points of a graph, and you'll call that something else when you take calculus, but for now we'll call these turning points. And by a turning point, I mean a point where the graph changes direction. So at each of these blue dots, the graph is either changing from decreasing to increasing, or the other way around. In other words, the y-coordinates have stopped going down and started going up, or have stopped going up and started going down. So this graph has 4 turning points. And since we know what this is the graph of, we know the degree of this graph is 5. And so this is always going to be a relationship. And again, it's going to be a bound. It's not going to be the exact number. But in general, if I know how many turning points I have, so we call it t, then the polynomial has to have one more degree than that. So in this example, there were 4 turning points in degree 5. It's just because 5 is 4 plus 1. Just like before, we can make up an example where the degree is actually higher than that by having it sort of wiggle more somewhere else, or in a couple of other ways that we could do that. So we don't really know the degree is from the 4 turning points. We don't necessarily know that this has degree 5, but we know that degree has to be at least 5. All right, so let's try the idea here. Take a minute and identify the real zeros, so that corresponds to the horizontal intercepts of these two graphs, and then say what fact 1 predicts about the degree. The degree will be at least something, and then we'll do it again using the turning points. And I'll just let you do that, and then I'll fill in all the answers. So you might want to pause the video if you don't want to see all the answers. So you can see I've marked up the zeros in red on these two graphs, and then I've translated what fact 1 says. Fact 1 just says the degree of the polynomial has to be at least the number of zeros. So since the graph on the left has 3 zeros, that tells me that that polynomial must have degree at least 3. And since the one on the right has 2 zeros, that tells me the degree of the polynomial on the right is at least 2. The one on the right is the one that is definitely not going to be exactly degree 2 for sure. Degree 2 polynomials are parabolas, and this has got some kind of other wiggling stuff in it. So the one on the right is a good example of why the other criteria is actually better, because it's going to base our prediction about the degree on how much the graph wiggles, not just where it happens to cut through the x-axis. So let's now go to the next thing and estimate the turning points, and then write down what fact 2 predicts. And again, I'll let you do it, and I'll check answers, so you might pause the video if you don't want to see the answers all at once. Okay, so here again I've written in my, my answers to this. The green dots that I drew on the graphs are where the turning points are, and I try to estimate those. Those don't seem to fall on nice numbers, so however we want to estimate is good enough. But I can see the graph on the left has 2 turning points, and so fact 2 says its degree should be at least 3. The degree should be at least 1 more than the number of turning points. And notice how that's consistent with what we said before. So in some cases you get the same analysis, the same prediction. The graph on the right is the one where we get a better answer. It was true that the graph on the right is definitely degree at least 2, but because we see 3 turning points on the graph on the right, we know the degree really is at least 4. So it's not incorrect to say at least 2, but it's a better answer to say that the degree is at least 4. And in fact, if you were to, since I drew these graphs, I know what the underlying polynomials were, and if it, just so you know, the one on the left really is a degree 3 polynomial, so those two predictions matching up make sense. The one on the right is actually is a degree 4 polynomial. Now keep in mind that either one of these could have had a higher degree if I had been sort of sinister about constructing them. But this at least gives you a general idea of what a degree 3 and degree 4 polynomial look like. And it gives us a nice tool, especially this idea of counting the turning points, gives us a nice tool for taking a graph and being able to make a prediction about what degree that should be.